Hello everyone, welcome to the 2020 National Home Performance Virtual Conference. My name is Russell King. I'm a mechanical engineer. This session is called Residential HVAC Design Basics. Our agenda for today is a brief introduction. We will discuss the HVAC design process, kind of give you a brief overview of that process, and then we'll do an example house. So you're probably wondering who the heck I am and why we are here. We'll talk about that, and then we'll go over ACCA manuals J, S, and D. My name is Russell King, as I mentioned. I'm a mechanical engineer. You can call me Russ. My license is good in 3 different states: California, Nevada, and Hawaii. I started doing ACCA residential mechanical design back in 1988, right out of college. I was using a computer that didn't even have a hard drive. It had 2 floppy disks that you had to swap back and forth. But actually, when I first started doing ACCA designs, I was not using a computer. It was manual. Manual J was literally manual. It was a worksheet that you had to fill out by hand, and if you got halfway through and realized you made a mistake early on, you had to go in and do a whole bunch of erasing. During my career, I started and ran mechanical engineering departments for 2 different companies. Started them from scratch and built them up to pretty good size. That was from 1998 to 2009. Both of those companies probably accounted for 3,000 plans that I did over my career at those 2 companies. For a while, I was the director of ACCA's West Coast office from 2009 to 2011. Basically, I represented ACCA out here in California and represented them at some government hearings and things like that. I have an HVAC blog called russellking.me. That's an actual internet extension. I think it works because I'm a mechanical engineer. I think it's supposed to be me for people who like to write and talk about themselves, but I don't. It's just russellking.me, and I talk about a lot of residential HVAC design topics, and then I also have a book called HVAC 1.0 Introduction to Residential HVAC Systems. It's a very basic book. It's used as a textbook in a couple community colleges out here in California for their HVAC and trade school programs. So ACCA manuals J, S, and D. You've probably heard of those before. You might be familiar with them. ACCA, ACCA stands for Air Conditioning Contractors of America. They are the largest HVAC trade association in the United States. They write and publish ANSI approved manuals. ANSI is a very precise approval process that different organizations have to go through to show that they're the steps that they take to review and approve something is very official. And the manuals they do are related to residential and non-residential HVAC design. They're widely recognized as the standard for how to do residential HVAC design, but they're not the only standard. There are some others out there. ASHRAE is one, but I would say manuals J, S, and D are probably by far the most commonly recognized standards. In fact, some building codes actually require manual J and D or equal for all new residential HVAC systems, and you're probably starting to see more and more of that. At least block loads, manual J block loads are required, but some building departments will require mechanical plans and manual J and manual D calculations. So manual J, S, and D. Manual J is residential load calculations. Manual S stands for equipment selection. And manual D is duct design. There are lots of other manuals. The other 3 that you might find useful are manual RS is a overview of residential system design. Manual T is for terminal selection. That guides you through the process of reading manufacturer specs for supply registers and return grills. Manual H is a good one. That's about heat pumps. You'll probably start seeing a lot more heat pumps as we start to go into electrification of homes. And then there's lots of other things that ACCA puts out. Some of the most useful ones are their standards and checklists. They have a standard called the Residential QI, which stands for Quality Installation. They have a QM standard for quality maintenance and those types of things. So I encourage you to visit their website, www.acca.org. So manual J, residential load calculations. It's basically a bunch of tables. The vast majority of this book, that's probably an inch and a quarter thick, is tables, and these tables are numbers. Most of them are what we call heat transfer multipliers and cooling transfer multipliers, and it's basically a simplification of the UA delta T calculation to calculate heat transfer into or out of a surface in the home, such as a wall or a window or a ceiling. And there's two basic types of calculations that you can do. One is called a block load, and that's basically the entire house or the entire zone that will be served by a single system, all done as one single heating and cooling load calculation. But if you're going to design the ducts for a house, you really need to know how much air needs to go into each individual room. And to do that, you have to do room by room load calculations to determine, how much room, how much is the load on this room compared to this room compared to this room, and so on. Manual S, equipment selection, basically guides you through the process of determining the actual heating and cooling capacity of the equipment that you're choosing to meet the loads of the house that you calculated using Manual J. So Manual J is the what the house needs. It's the demand of the house, if you will. And then Manual S helps you determine the capacity or the supply. How much cooling and heating capacity does the equipment supply to meet the demand of the house? It provides guidance on how to determine the output capacity of HVAC equipment at design conditions. So design conditions are the conditions that the equipment will actually be operating at when it's installed in the actual house, as opposed to the conditions that the equipment is tested at when the manufacturer says, oh, this is a 4-ton piece of equipment, or this is a 3-ton piece of equipment, or this is a 45,000 BTU furnace. When they get those numbers, the equipment is tested at basically at laboratory conditions, and they're very precise, controlled conditions. But that's not what the equipment's going to see when it actually gets installed. And so Manual S, especially for air conditioners, Manual S will help you read the manufacturer's specifications and determine what the actual capacity is going to be at design conditions. The conditions that are important to understand and the numbers that you need to know are fan airflow. How much is that air handler going to move when I put this kind of duct system on it versus this other kind of duct system? What's the heating capacity going to be? And then most importantly, or the most complex calculation is determining cooling capacity. There are two kinds of cooling capacity, sensible and latent. Sensible capacity is the ability of the air conditioner to change the temperature of the air, and the latent capacity is the ability of the air conditioner to dry the air, to remove moisture from the air. And those two together add up to the total cooling capacity. So when we talk about a 3-ton or 4-ton or 5-ton piece of equipment, that's the total capacity, sensible and latent. And that number will actually change depending on different things. So air conditioning capacity depends on the outdoor temperature. What's the temperature that condenser is sitting in, and it has to dump those BTUs from the house to the outside, and the hotter it is outside, the harder it is to do that. So the hotter it is outside, the capacity goes down. The other thing that's important is the indoor temperature. How cool is it inside? And how humid or moist is the air inside the house. So the wet bulb and the dry bulb temperature come into play and help you determine the actual design capacity of the equipment. But one that a lot of people don't pay enough attention to that has a big impact on the air conditioning capacity is the airflow. How much airflow is blowing across that evaporator coil, and what affects airflow? Duct sizes affects airflow. Then Manual D, sizing those ducts, designing that duct system. Manual D provides methodology for sizing ducts based on the available static pressure. So the static pressure is what the fan provides you. The central system fan, the air handler, whatever you want to call it, that fan provides a certain amount of airflow at a certain resistance, and that resistance is quantified as pressure. So how much pressure is that fan working at? As that pressure goes up, airflow goes down. And that pressure goes up because the ducts get smaller or more twisty and turny and longer and things like that. Manual D provides methodology for sizing ducts based on the available static pressure and the desired airflow. How much airflow do you want to move through that duct? And then the other thing that comes into play is the type of duct material. Is it flex duct? Is it rigid duct board? Is it sheet metal? Those all have different friction numbers according to the duct type, and that will change the size. So it might take you a size bigger to move air through a flex duct than through a sheet metal duct, because sheet metal duct is much smoother. So now a quick overview of the overall HVAC design process. So something you have to realize from the beginning, assumption number one, a well-designed system is designed to be controlled automatically by the thermostat to maintain a set temperature, not by the homeowner. Okay, so that's very important to understand, is that we are designing a system to operate at steady state conditions, and what that means is things are changing very, very slowly. The outdoor temperature is rising to its highest point and then dropping down to its lowest point. It's going up and down, but it's doing that very slowly. And the indoor temperatures are staying very constant. You might have unoccupied times and occupied times, so there might be a setup and a set back temperature, but other than that, the temperature is staying constant. We are designing to those conditions. If the homeowner is not willing to operate a house at those conditions, then it's a completely different situation and it's just not going to work. So a big part of HVAC design is educating people who are going to operate those systems. So I'm going to sprinkle throughout this presentation what I call rules of thumb. Rules of thumb have gotten a very bad reputation, so I'm going to call these Russ's evil rules of thumb. But I think that reputation is undeserved. If you look up the definition of a rule of thumb, it says that a rule of thumb is a broadly accurate guide or principle based on experience or practice rather than theory. So I think that to me sounds like a pretty good thing. So a good rule of thumb is actually a good thing. The problem is what some people call rules of thumb are just really, really gross oversimplifications that get them into a lot of trouble. The best example I can think of is, the 500 square foot per ton. Oh, I size my air conditioner on 500 square feet per ton or 400 square feet per ton or whatever that number is. That's a gross oversimplification of how you size an air conditioner, and it just doesn't hold water at all. And people call that a rule of thumb. It's really not. It's just a bad practice. Some rules of thumb actually work pretty well, and they're guidelines, and as it says here, broadly accurate. Anyways, I'm going to throw some in here. They're mostly for just discussion purposes. The first one, oversizing an air conditioner can cause more comfort complaints than undersizing an air conditioner. So a lot of people think that well, bigger is better. I'm not sure how this homeowner is going to occupy this house, how they're going to use this system, so I'll put in a little bit of extra capacity. But what that ends up doing is actually causing more comfort complaints. Most of the comfort complaints that I deal with, that I run into, those systems are oversized. It's a combination of undersized ducts and oversized air conditioning equipment. Just leads to all kinds of different comfort complaints, and people will tend to think, oh, it must be undersized, that's why I'm having these complaints, but the problem is actually that it's oversized. All right, assumption number two when designing an HVAC system: a well-designed system is designed to maintain a certain indoor temperature when it is a certain outdoor temperature. So there's two temperatures that come into play, the indoor temperature and the outdoor temperature. And the difference between those we call the delta T, the design delta T. These temperatures, the indoor temperatures and the outdoor temperatures, are set by ACA. There's recommended numbers for those, and there's also, in some states, there's code, like California very precisely sets the indoor and the outdoor temperature. The outdoor temperature depends on the city, so you're gonna have to look that up. You're gonna have to find a table. ACA has a table, there's other tables available, and it will show the design temperatures. If you want more information about that, if you want to go into more detail, I have a blog article called What's a Few Degrees Amongst Friends, and there's also a chapter in my HVAC book that covers what difference does it make if you were to bump up your outdoor temperature by a couple degrees when you design your air conditioner. It's not as big as you think. The process: when you're designing an HVAC system for a house, there are 4 basic steps. The first step is to collect the information about the house. You need to know about the house. You can't just have the square footage. You can't just have, the direction it's facing. You have to know the number of windows, the type of walls, and all that kind of stuff. The next step then, once you have all that information, you perform room by room load calculations. Now, back in the old days, we used to do that by hand. We used to fill out a worksheet and we would look up a number in a table. We'd put the number in the worksheet and we'd calculate it out. And nowadays we have computers that do all that for us. That's good and bad, but we'll talk about that. The next step, once you do your load calculations, and remember the load calculations is what the house needs. The next step is determine a piece of equipment that's going to meet those demands, those loads. And so that's step 3, select equipment to meet the total loads. Then once you have that equipment, you'll be able to determine the total airflow that equipment provides at ideal conditions, and then you use that number to design the distribution system, the ducts. So step 1, collecting information about the house. If you're designing a system for a brand new house, most of the information you need is going to be on the building plans. And if you're in a state that has energy codes, there will be some energy compliance documentation that will tell you the kind of windows, the kind of walls, the insulation, and all that kind of stuff. And so you can get it from there. So the information about a brand new house should be pretty readily available. This will also provide you with the floor, wall, ceiling, and door and window areas and orientations that you need, because you're going to have to do plug those numbers into a software program that will do the calculations and that will calculate how much heat is conducting into the house in the summertime and out of the house in the wintertime. The goal of collecting information about the house is to have enough information so that you can accurately estimate the conduction, the convection, and the radiation heat transfer between the inside and the outside of the house. If you are designing a system for an existing house, you might have to create your own plans by sketching a floor plan based on field measurements. So you might have to go out to the house with a tape measure and measure the perimeter of the house and draw the floor plan, and hopefully it looks a little better than this one. But the good news is if you have something like this with all the information that you need, you can do load calculations with something even kind of sloppy like this. Once you know all the physical dimensions of the house, the next thing you need to know is the qualitative stuff. What kind of wall is it? How much insulation is in that wall? What kind of windows? What's the U factor? What's the solar heat gain coefficient? Okay, and then there's some things you're just not going to be able to determine very easily unless you measure them. You're going to have to make some engineering decisions about duct leakage and infiltration unless you can measure those directly. Whatever assumptions you use, they need to be verifiable in the field when possible. For example, if you assume that the house has tight ducts and they're not, your system might be undersized. You may have way underestimated the load from the leaky ducts and you assume tight ducts, so that could be a problem. You can also go in the other direction. You can assume loose leaky ducts, but they're very tight. Now your equipment is oversized, and remember, oversizing can cause just as many, if not more, comfort complaints as undersized equipment. It's always a good idea, if you can or can have somebody do it for you, is to verify things in the house such as duct leakage, and the other big one is infiltration, doing a blower door test on the house. We call that diagnostic testing. That's going out to the actual house and measuring those things. If you can get that information, that is great. If you don't have that information, your margin of error becomes much higher potential to be off. Okay, infiltration can be one of the largest single sources of load, especially on the heating side, and so it's very important that you know that as best as you can. Another rule of thumb, don't waste time splitting hairs when your job is to shave heads. And what that means is there's a lot of detail, there's a lot of things you're going to have to make some guesses on, there's a lot of data you're going to have to input into the software, and I have literally seen people just stop in their tracks because they couldn't figure out what number to put into a certain box in the software. They didn't know. The software was asking them, what's the color of the roof, dark, medium, or light, and they're like, I don't know, what is dark, what is light, what is medium, I don't know, haven't been out to the house, and they kind of freeze up. Well, you got to pick something in the middle and move on. Your job is to shave heads. You got to get going. You got a lot of data you've got to enter, and you're going to get to your final point where you've sized that equipment, and then you can go back and evaluate where you are. Does that seem reasonable? Does it seem logical for this particular size? Any one particular data point is not going to make or break your entire design, and you don't want to always guess high and you don't want to always guess low. You always kind of want to be in the middle where it's verifiable and justifiable. Another rule of thumb is actually a saying that I really like by John Maynard Keynes. He's apparently a famous British economist. His famous saying is, "It's better to be approximately right than exactly wrong." And I love this because I find people spending way too much time splitting hairs. Like I was saying, they stress out on getting things just right. And after you've done enough of these designs, you'll start to realize what's important and what's not important, and you'll learn where to spend your time and where not to spend your time. And don't worry about the nitty-gritty details. Just move on. Get a good design, make sure it's working well, make sure your design is justifiable, make sure it's reasonable, and go from there. Step 2 in the design process, once you've gathered all the information about your house, you need to plug that data into the room-by-room load calculation software. There are two basic kinds of load calcs. I briefly mentioned these earlier. The first one is a whole house load calculation that basically lumps all the house into one total value, or zones if there's more than one piece of equipment. So each section of the house served by a piece of equipment, we call that a block load. Okay, that's used to determine the size of the equipment that's going to serve that house or that portion of the house. But if you're going to do duct design, you need to know room by room load calculations. So that's the other kind of load calculation. One is just more parsed into individual spaces, and the other one is just totaled all together. If you do room by room load calculations, obviously you can just add those up to get your whole house. But if you only do a whole house load calculation, it's pretty tricky to then parse that out on a room by room basis without actually calculating room by room loads. Room by room load calculations are very important for designing a distribution system. The industry standard for performing load calculations is ACCU Manual J. It used to be a series of tables and worksheets that allowed a designer to perform the calculations by hand. Now those tables are incorporated into one of several programs written by private companies. So there's several of those out there. We're going to do an example house later using one of the newer ones that's available. Just realize that there's a big book somewhere that has all these tables. So when you plug a number into the software, such as window area, and then you tell it what kind of window that is, it looks up in a table to multiply that area times a number to give you heat loss or heat gain through there. So there's a lot of math going on in the background, and the software does that for you. Now, as I mentioned, that's a good thing and a bad thing to have software. Software does the calculations very quickly and very accurately. You can do a load calculation, and then the really cool thing is you can go in and change something. You can say, okay, what happens to the load calcs if I change the window? If I go from clear windows to low E windows, how much does that affect the load calculations? And you can do that very quickly and very accurately. The problem with using computers and software, if you've heard the expression garbage in, garbage out, if you don't do a good job entering the information, it'll do a very precise, very accurate calculation on that garbage, and it will give you garbage right back. So do be careful, do check your work, do know how to print out the reports and go through them and check your work to make sure everything looks good and looks reasonable. So there are two load calculations, one for heating and one for cooling. The winter is calculating the heat that's leaving the house. It's warmer inside than it is outside, so the heat is escaping. Heat always goes from warmer temperature to cooler temperature, and in the wintertime it's warmer inside than it is outside, so the heat will be leaving. In the summer, the opposite is true. It's warm outside and cool inside, so the heat is coming into the house. So those are two different load calculations. Each one has two different temperatures that the indoor temperature and the outdoor temperature that affect those load numbers or that amount of heat transfer. Let's look at heating load calculations first. They're actually the easier of the two to understand. A heating load calculation is a sum of all the BTU losses. Those BTU losses can either be in the form of convection, which is heat transferred through moving air, or conduction, which is heat transferring through a solid object, or radiation, heat transferred by means of electromagnetic radiation. A good example of radiant heat energy is sunlight. So the radiant heat gains on a house are very important. That's the sun shining through the windows. These all occur when it's a certain delta T. So there's an indoor temperature and an outdoor temperature that drives BTU transfer through a surface. Radiation, it's important to point out that it is not affected by the delta T. Radiation will happen at approximately the same rate regardless of the outdoor temperature. The delta T is determined by two temperatures called the winter indoor and outdoor design temperatures. For heating, these occur at night. Okay, solar gains help the heater, so they're ignored. Also, if you think about it in the wintertime, when does the coldest temperature happen? It's usually at night. So that's the assumption, is that you're not going to factor in solar gains when you do a when you do a heating load calculation for the wintertime. Cooling loads are similar, except they are more complicated because solar gains are not ignored. Solar gains are a very big part of cooling loads. That's the sun shining into the windows, that's the sun beating on the roof of the house and that heat getting into the attic, that's the sun shining on the walls and warming up the walls, but mostly it's windows. Okay, so solar gains are a significant contributor to the cooling loads. What makes them so complicated is that solar gains are affected by not just the size of the windows, but the orientation of the windows. What direction are they facing? And is there any shading on those windows? Are there overhangs? Are there drapes, roller blinds, mini blinds inside? Those can all reflect the heat. Overhangs can block the sun before it even hits the window. So all those come into play and make cooling load calculations much more complicated than heating load calculations. Once the room-by-room loads are done, they can be added up to get the total heating and cooling loads. That's our block loads. Once you have your block loads, then you can select your equipment. If it turns out that the total heating or cooling load is too large for a standard piece of residential size equipment, the house can be broken into smaller zones. Or you can go to commercial equipment, but typically they will just break the house into smaller zones. And then you can do separate block loads for different parts of the house. A very common example of that is larger two-story homes. The total load of the house might be too big for a 5-ton piece of equipment, so they will split it between upstairs and downstairs, and the upstairs block load, the downstairs block load, and you'll have two separate pieces of equipment to handle those two zones. Step 3 then is selecting the actual equipment to meet those loads. So you have your heating and cooling load calculations. Now you need to pick a heater and an air conditioner to meet those loads. Well, selecting a gas furnace to meet the heating loads is quite simple. That's a very common type of equipment used in the United States. The vast majority of designs that I've done have been gas furnaces, but you're starting to see a trend towards electrification, more heat pump heating systems. But if you do have to pick a gas furnace, it's quite easy. You'll have a heating load number, and then basically you just pick a furnace with a output capacity that's just slightly higher than that load. The output capacity is relatively not sensitive to variations in design conditions. One of the things that you do have to adjust furnace output capacity based on is altitude. As you go up higher in altitude, the capacity is a little less because the density of the air is different. But other than that, furnaces are pretty much dumb beasts. You have a load and you pick a furnace that'll give you a load slightly higher than that. But don't forget that your furnace is your air handler for your air conditioning system. So another very important part of selecting a furnace is not just meeting the heating load, but making sure that it provides enough airflow to handle your cooling load as well. If your furnace does not have enough airflow, you may have to pick a bigger furnace than what you need for your heating load. You might actually have to oversize your furnace. On the heating side, oversizing equipment, it doesn't cause quite as many problems as oversizing cooling equipment, but it still potentially can cause issues, so do be careful with that. Don't go too big on your equipment, but you do have to get airflow. You may have to change the brand of equipment or the line of equipment in order to get more airflow without so much heating capacity. Selecting a heat pump, on the other hand, is more like selecting an air conditioner. There are more things that come into play. Airflow, outdoor temperatures, and things like that do affect the heating capacity of a heat pump. So if you're going to get into that, which you probably will, ACCA Manual H will help you with sizing heat pumps. The overall process is somewhat similar to selecting an air conditioner. Selecting an air conditioner is much more complicated than selecting a gas furnace. This is all covered by ACCA Manual S. Air conditioner capacity, which is its ability to cool. Okay, you have to keep capacity and efficiency separate. Capacity is how much cooling it provides. Efficiency is how much energy does it require to provide that capacity. But capacity is its ability to cool. An air conditioner's ability to cool is affected by several things. It's affected by the outdoor temperature. What is the temperature that that condenser is sitting in to which it has to dump heat? All that comes from the manufacturer's data tables, the specifications for the equipment that you're looking at. The other factor that's very important that a lot of people don't take into account as much as they should is the airflow. The amount of air blowing across the evaporator coil. The evaporator coil is the coil that's in the indoor airstream that's transferring the heat from the air into the refrigerant, which is then carried outside and dumped outside at the condenser. So the amount of air blowing across that coil affects the capacity of that equipment. As the airflow goes down, its ability to remove that heat goes down and the capacity goes down. So capacity of an air conditioner is proportional to the airflow blowing across that coil. So airflow is very important. The other thing is, what is the indoor temperature? This is normally set by code or by ACCA. They suggest for cooling that the indoor design temperature be 75 degrees. That's the indoor thermostat set point. So 75 degrees inside, whatever it is outside for that city, that's your delta T. And then whatever your airflow is, that's very important. But then also how humid is the indoor air, because as I mentioned earlier, there are two kinds of cooling. There's sensible and latent cooling. Latent cooling is the air conditioner's ability to remove moisture from the air, and the more moist the air is, the more it has to work to do that, and which reduces potentially the ability for it to cool air. So all four of those numbers come into play. You can plug those in to a spreadsheet. There's software that helps you do that, but the answer is going to depend on those four numbers and the brand, the make and model number of the equipment that you're looking at. Okay, for outdoor temperature, indoor temperature, and indoor humidity, there are standard numbers that are commonly used for those, set by ACCA and set by code. So those are fairly standard. The airflow is very important, and what sets the airflow is how you design the ducts, and that's what we're going to do. So the fact that we're designing the ducts to maintain a good airflow is what makes residential HVAC design work. Here's another rule of thumb that I like to suggest to people during my trainings that I do. Never design an HVAC system for a crappy house. I have people calling me up and saying, hey, these homeowners have a house with no ceiling insulation in it. The house is super leaky and it's a small house and the load's coming out really high and they want a big air conditioner for this house. And I say, if you do that, you're not serving that homeowner. They need to fix the house before you do your load calculations. Or you can design assuming that they're going to improve that house, install that system, and then let them approve the house down to the size of the air conditioner. But do not design an HVAC system for a really crappy house. You're not serving the homeowner when you do that. Step 4, designing a distribution system. This is one of the most overlooked aspects of HVAC design. This is where people use what a lot of people refer to as rules of thumb. It's not really a rule of thumb, it's more just a gross oversimplification. So they'll say, oh, it's a bedroom, I always put a 6-inch duct in a bedroom. Oh, it's a kitchen, I always put an 8-inch duct in the kitchen. And if they do that, they're just oversimplifying the process and doing a really bad job. So there's a lot more to it than that, obviously. Historically, and installers have relied on rules of thumb, and trial and error is another way to another way to design system is, oh, it didn't work this time, let's fix it next time, let's put in a bigger system next time. So you'll see a lot of that as well. The industry standard for residential duct design is ACCA Manual D. The concept of ACCA Manual D is not very difficult as long as you have room by room load calculations. Okay, consider the following layout. So here we have a very simple HVAC layout. This is a very typical system that we see out here in California and the Nevada area and a lot of places out west and maybe even down south a bit. Horizontal furnace up in the attic with ducts in the attic and ceiling registers. So over here you'll see that S stands for supply, R stands for return, and T stands for trunk. Okay, so S1 is supply register 1, S2 is supply register 2, and so on. So these are all supply registers. R stands for return, so there's return number 1, and a second little return over here. Let's say this is in the master suite or something like that. Okay, T stands for trunk, so we have 2 supply registers and they're served by a trunk. So a trunk is a duct that splits again into more than one duct, and a branch is the final run out that goes out to the supply register. So we have 1, 2, 3, 4 supply trunks. You could have return trunks as well, but we don't in this example. Notice I don't mention what these rooms are. It doesn't really matter what these rooms are. What matters is what is the load on these rooms. The load will take into account the types of rooms that these are. If one is a kitchen, then you should have put extra load in that kitchen for the stove and the oven, what we call internal gains. Some of these rooms might have people in them, so that's how you account for what kind of room it is. That will all be factored into the load of the room. So all we really care about is the numbers associated with each one of these supply registers in terms of heating and cooling load. Our job is to size these ducts to make sure we get the right amount of air to each one of these rooms. So the first step is to figure out how much air needs to go to each room, and then we have to figure out how big these ducts need to be in order to provide that air. So I'm going to give you some example room by room cooling load calculation numbers for each one of those rooms. Keep in mind that these numbers are rounded off just to keep the math simple. In a real load calculation, you'll get a load calc for a room that's something like 1237 BTUs per hour, but I'm just going to round those off to nice round numbers like 1200. So just be aware of that. It's just to make this example easier to follow. Note that cooling load calcs are typically used to size ducts, not heating loads. And the reason is because the air handler in cooling mode will run on a higher fan speed than in heating mode. For example, a typical furnace might have 4 speed taps. There'll be high speed, medium high speed, medium low, and low speed. And it will typically run on high speed for cooling and then one of the lower speeds for heating. That's very common and very typical. So if you're moving more air in cooling mode on high speed, that will generally drive the size of the ducts. But as we'll mention later on in a later slide, occasionally in an individual room, the load might be such that it needs a lot more air in heating mode than it does in cooling mode, and the need of the room, the individual room, for heating could be higher, and you might have to size the duct for that slightly higher airflow for heating than for cooling, but we'll talk about that more. So here's some example load calculations. So let's say we were using a software program and we plugged in all the information about the house and we did our load calculations, and this is what comes out. Okay, room S1 or supply register 1 has a heating load of 2600 BTUs per hour. This room 1800, this room 3800, and so on. So you can kind of look at these and say, all right, this one's a lot higher than this one. So this might be a bathroom, this might be the kitchen or something like that, but it doesn't matter. These are the important numbers right here. The other important number is what do they add up to? What is your total? So we have a nice round number here of 24,000 BTUs. So I'm going to skip the manual S steps and just tell you that this is probably going to be a 2.5 ton piece of equipment. When we do our example house later on, we'll go through some more detail. Obviously this presentation is only a couple hours and it's not intended to be in great detail. It's just intended to kind of give you an overview of the process, and as the name implies, it's basics, residential HVAC design basics. So to learn how to size equipment, you're probably gonna have to take a class on Manual S or read Manual S itself. But I'll just tell you that this load right here, these are sensible loads by the way, will probably be a 2.5 ton piece of equipment. So another rule of thumb is you hear the term air balance a lot. Oh, this house has bad air balance, or we need to balance the system, do air balance on the system. Well, air balance is just another way of saying that each room needs its fair share of air. Fair share of air means that each room needs an amount of air that's proportional to that room's load. In other words, if a room is twice as much load as another room, it should get twice as much air. If a room is 10% of the total load, it needs 10% of the total air. So our first job is to look at each room's load and see what percent it is of the total load. So the next step is to determine what percent of total each load is. This can be a decimal. I will call these percentages, but they're really just decimals. To find this number, just take the individual room load and divide it by the total load. Very simple math. And again, this is all done internal to the software, but it's important that you know this process and how this process works. Okay, so for example, S1, the room S1 had a load of 2600 BTUs. The total load was 24,000. So we take 2600, take the smaller number and divide it by the big number, and you get a number like 0.108. So basically that means that room S1, if you convert that to a fraction, or I'm sorry, to a percentage, is 10.8% of the total load. So room S1 is 10.8% of the total load, which means it needs 10.8% of the airflow. So that'll be the next step. So first we have to find the percent of total for each room. It's a very simple calculation. You take the load of the room and you divide it by the total and you get your fraction or your percent. Okay, 2600 divided by 24,000 is 0.108. 1800 divided by 24,000 is 0.075. 3800 divided by 24,000 is 0.158, and so on and so forth. Something that's important to do if you do this calculation by hand is to add these all up and make sure that it adds up to 1. If it doesn't add up to 1, hopefully it's just off by a little bit. If it's off by a lot, you need to redo your calcs, but if it's off by just a little bit, it's probably just a round off error, and you can adjust one of these numbers to make up for that, but it should add up to 1. In other words, 100%. Now let's assume that the equipment selected delivers 1000 CFM of total airflow. Again, that's a manual S thing, and we don't have time to go into a lot of detail on that. Suffice it to say that a common design criteria is 400 CFM per ton. That's usually a decent starting point, and then you'll fine-tune that based on the actual equipment. And so we've decided this would be a 2.5 ton system. So 2.5 times 400 is 1000 CFM. So that's how we're going to start our design. When we pick an actual furnace, an actual air handler, it might be a little more than that, it might be a little less than that, and we can adjust accordingly. But this is a good starting point. So the airflow must be distributed proportional to each room's load. So we calculated the percent totals for each room. Now all we have to do is multiply those numbers, the percent or the fractions, the decimals, times the airflow. So if you remember for S1 it was 0.108. So if you multiply that times the total airflow, you get 108 CFM. So in other words, that room was 10.8% of the total load. 10.8% of the airflow is 0.108 times 1000, or 108 CFM. So we just have to do that for each room, and then the same way we check to make sure that the load percentages all added up to 1, we have to make sure that all our CFMs add up to our total CFM of 1000. So here's our table, here's our numbers that we calculated. Now we just have to take each one of these numbers and multiply it times our total CFM of 1000 and write down the CFM for that room. Again, this is just an exercise. This is all done internally to the software and done very quickly for you, but it's useful to know how that happens and where those numbers come from. Okay, so 0.108 times 1000 is 108. 0.075 times 1000 is 75, and so on. Make sure you check that these all add up to 1000. So this table that we just filled out is each room's fair share of the total, which is 1000 CFM. This is very useful information. This is how much each room needs to be comfortable. This is each room's fair share of the air. Okay, and the only way you can really do this accurately is if you have these room by room load calculations. If all you had was a block load, you wouldn't have those numbers and you wouldn't be able to figure out how much air needs to go to each room. The next step, now that we know how much air needs to go to each room, is to size the supply branch going to that room. Okay, so that's the runout. That's the ducts that's attached to the supply register in each room. Before we do that, we have to talk about a fairly complex topic, and it's one that people misunderstand quite a bit. And when you size a duct, you need three things. You need to know what kind of duct is it. Is it flex? Is it sheet metal? Is it duct board? Okay, so this example is all flex duct, so we'll make sure we got that straight. The next number you need is your airflow. How much air are you trying to move? And then the third number you need is something called a friction rate. And a friction rate is the number used to size ducts, and it's calculated for each system based on that system's design static pressure, pressure losses, and total equivalent lengths. Okay, so any given duct system, the friction rate is probably going to be slightly different than any other duct system. Okay, it depends on the operating static pressure that you've chosen for the fan, where we got that 1000 CFM. That 1000 CFM, by the way, is an operating airflow at a certain pressure. That pressure is how much that fan will operate against and still give us 1000 CFM. So we need to design the ducts not to exceed that design static pressure. Okay, but different parts of that duct system eat up that pressure. They use it up. The evaporator coil eats up a lot of our pressure, and so we need to take those into account. And then another way that Manual D does a very good job of quantifying various parts of a duct system is through something called equivalent lengths. Equivalent lengths it can be actual length of a duct. How long is that duct? Is it 10 feet, 20 feet, 30 feet long? So that has a certain amount of resistance associated with it. But also a bend or a fitting of a certain type, different things along the way use up static pressure. But instead of quantifying them in terms of static pressure, they quantify them in terms of length of duct. So in other words, they say this bend is worth 10 feet of straight duct. So you add your 20 feet of straight duct plus 2 bends at 10 feet, so you get 40 feet total equivalent length. And so those numbers go in to calculating the friction rate, and the software that we'll do an example of later does a very good job sort of illustrating that. So once you know your friction rate, then your airflow and the type of duct, you can use a duct slide rule or what they call a ductulator, okay, and then look up the size of the duct that you need to deliver a certain amount of airflow. All right, so to keep it simple, we're going to use a very common friction rate of 0.1. That's common for a very simple duct layout like I've shown you. They could be a little bit higher than that, a little bit lower than that. The point is this is just an example, so this is what we're going to use, 0.1. That is a fairly common number. A more complicated duct system with longer runs and more fittings and more bends will have a lower friction rate. A shorter duct system, more simple duct system, will have a higher friction rate. The lower the friction rate, the bigger the ducts need to be. The units of friction rate are inches of water column per 100 feet. And basically what that means is that the friction rate for this duct system, for every 100 feet you travel, whether it's actual length or equivalent lengths of fittings, for every 100 feet of travel, you're going to drop a certain amount of pressure. And the lower the friction rate, the lower that pressure drop has to be as you go along. And in order to accommodate that, you're going to have bigger ducts. So friction rate represents how much static pressure can be used up as the air passes down the duct system. Lower friction rate means bigger ducts. Each 100 feet you go, you can only drop a certain amount of pressure, and in order for that to happen, you have to have bigger ducts. If you have smaller ducts, the pressure drops faster as you travel through the duct system. Another thing that you're going to have to keep a close eye on, especially out in California, they've just mandated MERV 13 filters in all new systems. That puts a big pressure drop on the system, so you want to make sure that you take that into account. So 0.1 is a common friction rate used for simple systems like this. Again, this is just an example. When you do an actual design, you're going to want to calculate the friction rate for that system, but it'll be fairly close to 0.1. It'll be a little bit higher, a little bit lower, depending on whether it's a more or less complex system than this one. So this little table here is an example of the numbers that you would get from a ductulator. Okay, this table is based on a friction rate of 0.1. So if your system does not have a friction rate of 0.1, this table is not valid. Okay, choose the size duct that provides the next largest airflow for what you need. So in other words, if you need 55 CFM, don't pick a 5-inch duct because it'll only give you 50. So you're gonna have to round up to the next size duct. In order to get the airflow that you need, you're gonna have to round up. If you're at 55 and a 5-inch duct only gives you 50, but look what that does. Now it gives you a 6-inch duct. That's the next available duct size up from a 5 to a 6. You need to move 55 CFM. A 5-inch won't do it, so you got to go to a 6. Well, a 6 can handle 80 CFM. So that's why people say that manual D has a built-in safety factor, because unless your duct design is calling for duct airflows or room airflows that are exactly what these provide, and the law of average will say no, you're going to fall somewhere in the middle of these. Okay, you might be slightly above this or slightly below that, but on average you're going to be basically in the middle of each one of these ranges. Okay, so you've got some built-in extra capacity. Like if you need 90 CFM to a room, a 6-inch won't do it. In fact, the software is so precise that if it's 1 CFM more than a certain size duct will handle, it will go up to the next air size. That's just how precise computers are by nature. Okay, if you need 81 CFM, it's going to round up to a 7-inch duct, which will give you 120. So there's some extra capacity there. Every system I've ever designed, when we went out and actually tested, it moved more air than what we designed it for. If we designed it for 450 CFM per ton, when we turned on that system and we went out to commission it and measure the airflow, it was always move more air than what we designed it to, more than the 400 CFM per ton. Okay, and that's why, because ducts only come in certain sizes, and unless ducts came in increments of tenths of an inch, there's some extra built-in capacity, and it's substantial. Look at the difference. Look at the difference between a 6-inch duct and a 7-inch duct. Okay, that's one available duct size. If you go to the store, you can buy 6-inch or you can buy 7-inch. Some places don't even carry odd number sizes, odd number size ducts. So they'll have 4s, 6, and 8s and 10s. They won't have 5s and 7s. So what if you needed 85 CFM and they don't carry 7-inch ducts? You've got to go to an 8-inch duct. So instead of 85 CFM, you're getting a duct that'll handle 170. That's a lot of extra capacity. I get run into a lot of contractors who just don't use odd size ducts, and so I say that's fine. If I call out a 7, round up to an 8. Okay, on the supply side, I've never ever had a problem with ducts being oversized. Okay, you get better airflow, your capacity goes up. There are some downsides to it. You get a little bit more surface area in a hot attic, so you might get a little bit more heat transfer, but overall it will work. In order for ducts to be too big, they have to be way too big. You have to need an 8-inch duct, but you put in a 14 or something like that. Okay, that's not going to happen typically. If you need a 6 and you put in an 8, you know what? That system's going to work great. It'll be fine. You can always make small adjustments later if you find out that you're just pushing. You're at 230, or sorry, if you're at 229 CFM. And it's calling for a 9-inch duct that'll give you 230. You don't have a lot of wiggle room there. You know what? Bump it up to a 10. Just tweak the total equivalent lengths of that run, change the friction rate a little bit, and bump it up to a 10. That's not going to hurt anything. That'll be fine. You can always do those kinds of small adjustments later on. As I mentioned, notice the difference between a 6-inch and a 7-inch duct. So the next available larger size from a 6 to a 7 goes from an 80 to 120 CFM. That's a 50% increase in airflow by going up 1 duct size. Okay, so hopefully that gives you some level of confidence to say, you know what, we're shooting at pretty big targets here. This is not rocket science. This is not brain surgery. We're trying to hit these pretty big targets, and as long as you're doing it right, as long as you're playing it safe and rounding up to the next size duct, you'll be fine. The system will work great. Here's another one of my rules of thumb, and this one you can live by. Okay, I actually ran into this one time. I had done a design, and I was calling. It was a two-story house, and I had a 12-inch trunk running from the attic down to the first floor. And on the plans, I called out very clearly that I needed a 12-inch clear chase because I needed to run a 12-inch duct straight down, and 12-inch clear means no obstructions, and that's even being a little iffy because don't forget ducts have insulation on them. Flex duct has insulation, so a 12-inch duct is the 12 inches is the diameter of the inner core that's moving the air, and then there's 2 or 3 additional inches of insulation on top of that. And so I was being generous in saying all I needed was 12 inches clear, and it was in a chase between the floors, so it was conditioned space. I was not too concerned about the insulation being compressed in a couple spots, and I knew that I was asking for a lot as it was, and so I just said very clearly I need a 12-inch chase. Well, what happens? I get a call from the installer, calls me up and says, hey, your design is all messed up. You call for a 12-inch duct coming down here, but there's not room for it. And I said, well, what happened? I called out for a 12-inch chase. And he says, well, there's a floor joist going right through the middle at the bottom. The framer installed a floor joist. I'm like, oh gosh, what do I do? So I called the framer. I said, hey, didn't you see my note on the plans? I called out for a 12-inch. I got to get a 12-inch duct down there. And he says, oh, why don't you just run 2 6-inch ducts? And I went, oh, great, here we go. All right, so here's my analogy. I told the framer, would you trade 2 6-inch pizzas for a 12-inch pizza? Would you trade 2 6-inch pizzas, 6 inches in diameter, for 1 12-inch pizza? And he thought about it, and he thought about it, and he said, you know what? 2 6-inch pizzas has twice as many slices as a 12-inch pizza. And I went, no, that's not how it works. And so I had to sketch it out for him. I go, look, 2 6-inch pizzas is not even close to a 12-inch pizza. 2 6-inch ducts is not even close to a 12-inch duct. So the cross-sectional area of the ducts is very different. The area of the duct is not proportional to its diameter, and the airflow is not even proportional to its cross-sectional area. Even if the cross-sectional area of 2 ducts is the same as 1 duct, that 1 duct will move more airflow because of the resistance of the surface area, the crust, so to speak. So even if this area plus this area equaled this area, this duct will still move more air because it doesn't have as much resistance to the air. In our pizza analogy, that would be the crust. Okay. All right. Did I make everybody hungry? We had our loads. We calculated our percents of totals. We multiplied those times the total airflow to get our room CFMs, and then we used that little table to size the ducts. And again, this is all done internal to the software, so this is just an example. So 108 CFM, if you were to look at that little table, find the next larger duct that will meet that is a 7, 6-inch, 8-inch, 7, 8, 9, 5, and 9. So there's our diameters of all the supply branches, the ducts that are attached to the supply registers. Okay, so that's pretty easy. The next step is to supply the trunks that serve those branches, and that's very easy. If we know the airflow here and we know the airflow here, to determine the airflow here, we just have to add those two together. So let's do that. If we know that S1 is 108 CFM and S2 is 75, we add those together, it's 183. And if we look on our little table, in order to move 183 CFM, we need a 9-inch duct. So that's what T1 is going to be. Trunk number 1 is going to be a 9-inch, and then these will be a 7-inch and a 6-inch. Okay, now I didn't know that when I sketched this up, and so I actually drew this TY wrong, so we'll have to adjust the drawing. Normally the trunk comes through, and if you look at a typical sheet metal TY that we use a lot out here out west, maybe out where you are as well, it's usually a cone of sheet metal with another little cone sort of tapped into the side of it. And typically what happens is the biggest duct will come into the bottom, and then if there's 2 branches that are not the same size, the larger of the 2 will be this straight run that passes through here, and the smaller of the 2 will be the one that comes off the side. So we've got a 9, 7, 6 TY. So this is the 7 as we've sized it, but the way I've drawn it is wrong. So what I need to do is redraw this so that this TY goes straight through here, sort of flip this TY around. So it goes straight through here and branches off to this small, because this is the 6 and this is the 7 and this is the 9. So 9, 7, 6. So this little TY is drawn wrong, but it's just a schematic diagram anyways, but your final design should be drawn correctly. So let's size all of our trunks. So trunk 1 is S1 plus S2. We did that one, 183. That's a 9-inch duct. Trunk 3 is moving 271. That's a 10-inch duct. Trunk 3 is a big one, 338 CFM, so that's a 12-incher. And trunk 4 is 208, so that's another 9. So those are 4 trunks on our diagram. Now the next step is to size the return ducts. To do this, you must assign supply registers to each return. So what you do is you determine where the air from each supply register is going to go. So you'll say the air from these supply registers over here are all going to go back to this return, and the air from these supply registers over here are going to go to this other return. So it just depends on where the supply registers are in relation to the returns. If there's only one return in the house, that's easy, they're all going back. But in our example, we have a second return, and I'll just tell you that that return is in the master suite. Also in the master suite is a supply register for the master bedroom and another supply register for master bath. So those 2 supply registers will go to that smaller return. All the other supply registers will go to the other return. Okay, so just determine which air is most likely to be drawn towards each return. If a return is behind a closable door, then all supplies on that side of the door should be assigned to it, such as our master suite example. Also, upstairs supply air should be assigned to upstairs returns, and downstairs supply air should be assigned to downstairs returns, but this is not mandatory. I've seen people go to too much trouble to try to get a downstairs return in a 2-story house. We don't have a whole lot of time to cover this, but let's just suffice it to say that it's better to have sufficient return upstairs than to worry about getting a return downstairs. Okay, that air will make its way upstairs to the upstairs return, and if you have good airflow and good mixing, it won't matter that you don't have a downstairs return. Okay, so one of the most controversial topics that I run into in residential HVAC design, the topic that people get the most riled up about, is where do you put a register in a room? Should it go back interior to the room, blowing across the room, or should you put it out over the window? Or like out in Las Vegas, they insist on putting registers dead center in the room. A lot of people over the years have put registers out over the windows, and a lot of people now start to insist on putting them more interior to the room, blowing out across the room. The rule of thumb I like to tell people is blow the air in the opposite direction that it wants to go. So if the air in a room, if you're blowing air into the room, the natural direction that air wants to go is out of the room, because you're pressurizing that room with air, so the air wants to leave. So if the natural path of air is to leave the room, blow the air in the opposite direction. Blow it from the door towards the other side of the room. What that does is it promotes mixing. The most important part of a supply register's job is to mix the air in the room. Okay, so blow the air in the opposite direction that it wants to go. A great illustration of this actually is a lot of people think that floor registers are better for heating because hot air rises. And so you've got your register in the floor, and the air is going to come out of the floor, and it's better if they're down low and you blow the air up. Well, that's actually not true. If you blow the air in the opposite direction it wants to go, then that means it's better to blow the air down. And what happens is hot air coming out of a floor register goes up, and it wants to stay up because hot air rises. So it's going to come out of that register, and it's going to go up to the ceiling, and it's going to stay there. But if you have a ceiling register and you blow the air down, the air is naturally going to want to rise back up. So by blowing it down first, it has to rise up past all that air that's being blown down, and it mixes. It mixes better. You get better mixing. You get more even temperature distribution. You get less stratification in the room. Okay, so blow the air the opposite direction that it wants to go. So as I mentioned, let's say that our example supply 7 and supply 8 are in the master suite, and this return 2 is also in the master suite, and there's a door separating this room from the rest of the house. So very easily we'll just say we'll assign these 2 supply registers to this return, and then all the other ones will go to the other one. So we add those up. Here's our return 2. Add those together is 208, so that's a 9-inch return. Add all the other ones together is 792, and that'll be a 16-inch return. Now, as I mentioned earlier, we started off sizing everything to the cooling airflow, but once you do the same thing for the heating airflows, you have to look at each room and compare the heating airflow to that room to the cooling airflow of that room, and pick the higher of the two. You want to size your ducts to the higher of the two. It occasionally happens that the heating airflow number will be higher, so it is worth checking. The good news is that the software does that automatically. You don't even know about it, and I will point that out when we do our example. Now take the sizes that we have, that we've figured out using our table and our airflows and our friction rate, and now label the duct sizes on the duct layout diagram. It's also a good idea, if you can, to write the target airflows next to each register so that they can be verified after the system is installed. One of the most valuable pieces of experience that I got in my career was we did a lot of designs for production homes, and we wrote the target airflow next to each register, and then we had people go out to the houses after they were completed and measure those airflows, and on the plans they would write the measured airflow right next to the number that were printed on the plans, and then they would send that back to us, and we were able to go through and look for problem areas. Occasionally we'd find one that was low. Most of the time it was caused by an installation issue, a duct being crushed or something like that, or maybe they had to run the duct farther around to get around an obstruction or something like that, and so the airflow was a little less than we needed. As long as it wasn't way under the target for that room, and as long as the total airflow for the system was good, we generally almost never had an issue. I don't think we ever did have a comfort complaint, as long as we met that criteria. So how does this system look to you? It's a 2.5 ton system moving 1,000 CFM. We've got a 16-inch main return with a 9-inch secondary return going to the master suite. We've got two 9-inch trunks, a 10-inch trunk, and a 12-inch trunk. I think a lot of people will look at that and say, that seems big to me for a 1,000 CFM for a 2.5 ton system. This probably is large for most systems out there if they don't do a good job sizing the equipment, and they're probably used to seeing smaller ducts than this. And this is what happens when you do a good design, and this system is going to work very well. Now we're going to do an example project using an actual software program and some actual house plans. This program is currently available. It's fairly new, and we're going to go through it start to finish. The software we're going to use for this example is called Hvac Model with Energy Gauge Loads. It is a software package containing Hvac Model 3D, which is a user interface, and Energy Gauge Loads, which is a load calculation engine, which is ACA certified. They run simultaneously and share data seamlessly. The process is that you build the house in 3D. You build a 3D model in Hvac Model, and then the physical dimensions of that model, the wall areas, the floor areas, the window areas, and the types of surfaces is transferred into the Energy Gauge Loads calculation module, which then performs the room-by-room load calculations. It will ask for some more information, and so we'll have to enter some more information into Energy Gauge. Energy Gauge then calculates the loads and walks you through the manual S equipment selection portion, and then once you select your equipment, all that information is transferred back into Hvac Model, and that's where you go and you size your ducts and you design your duct system.